All right, welcome to your first prerequisite for college algebra, and this is probably the most important thing that you're going to learn in college algebra. And I say that because it's just going to carry on with you throughout the year. You're going to have to come back and watch this video again, probably refresh yourself. This is something that we're going to use in every single unit, and that is factoring. What factoring is breaking down a polynomial or breaking down anything, a number polynomial, into its composite parts. You're decomposing it into a product of factors. What I mean by that, let me give you an example. If I had just the number 15, I could break it down into 3 times 5. You're breaking it down into things that multiply to get back to what you started with. Like I said, it's very important because we're going to keep using it throughout the semester. If you ever need to come back and rewatch this video, it'll always be here. I like to separate factoring methods based on how many terms a polynomial has, and so this is a good time to talk about terms. Terms in a polynomial or terms in an equation are always separated by a plus, a minus, or an equal sign. Since we're talking about expressions today specifically, we're just talking about pluses and minuses. But so, for example, this first one, we have a plus, we have a minus, that leaves us 1, 2, 3 terms. The second one has a minus, that leaves us 1, 2 terms. In expressions like this, if we had an equal sign, we would call that a separate term as well. But in expressions like this, anything separated by a plus or a minus is a separate term. The first type of factoring you want to try every single time is greatest common factor. The greatest common factor is the biggest thing that you can divide out of every single piece. So for example, if we have this first one, 4x minus 8, we notice it has 1, 2 terms. Can we divide both of those terms by the same thing? That's the question that we're asking. Can I divide 4x and divide 8 by the same thing? And yeah, we can. We could divide them both by 2 if we wanted to, but in this case, we're trying to find the greatest, the biggest thing we can divide them both by, and that would be a 4. We could divide them both by 4. If I divided the first one by 4, I would have just x left. If I divided the second one by 4, I would have a minus 2 left, negative 2. That's the factored form of this expression. A lot of times we're going to factor and then realize we can factor again. It's not always the case, but sometimes we factor it once and we realize, oh, we can do another step here. In these first few examples, we're just going to be able to do it one time. The second example, we've got 1, 2, 3 terms. Can we divide all those by the same thing? They're all even, so you can divide them all by 2. You can divide them all by 3. You cannot divide them by 4, but you can divide them all by 6. I think 6 is the biggest thing you can divide them all by. They also all have x's in common, right? The way you look at these exponents, since this one's x to the fifth, that's the same thing as 5 x's. 1, 2, 3, 4, 5. This one has 4 x's. 1, 2, 3, 4. This one has 3. 1, 2, 3. What's the most amount of x's you can take out without overdrafting? You could take out 3, right? I can take 3 out of here. I can take 3 out of here. I can take 3 out of here. That's the most I can take out of all of them. So my greatest common factor here is 6x to the third. If I took a 6x to the third out of this one, I would have, dividing, remember, 2. If I took out all 3 of those x's, I would have x squared left. I'm keeping the same signs between these things. If I took a 6 out of this, I would have 3. And if I took x to the third out, I would have 3 fewer. I would have just a single x. If I took 6 out of this, I would have negative 4. And if I took all 3 x's out of here, I would have no x's left. And so that is my factored form of that expression. GCF is the first thing you want to do every single time. After that, you'll start to look at how many terms it has. Here are some more examples. You can go in and do those, and I'll leave you the answers after this slide. All right, after GCF, you're going to look and see how many terms your polynomial has. These are just examples on this page. So 2 terms might look like this. 2 terms might look like this. Notice both of those examples have 1, 2 terms, 1, 2, or 1, 2, 3 in the 3 terms column. After you've taken the GCF, if you're still left with 1, 2, 3, 4 terms, you're going to look in this column, right? We're separating it by terms, and the methods that were used are these. I would absolutely take a second and write this down. You're always doing the GCF first. Then if you have 2 terms, you're either going to do difference of squares or cubes. You're going to try those 2. If you have 3 terms, you're going to try star. And if you have 4 terms, you're going to try grouping. So we're just basing this based on how many terms a polynomial has. We'll look at an example of 2 of each of these, but remember that we're always going to try GCF first, and then we're going to look at how many terms there are to determine which method we're going to try. All right, first example here, we've got x squared minus 9. Can we take a GCF out of those? We cannot. There's not anything in common between those two. It has two terms, and so we're looking at, if you look at your chart, either difference of squares or we're looking at cubes. These look like squares, and I know something's a square if I can take the square root of it. On your calculator, if you take the square root of 9 and you just get a 3, a regular old 3, not with a decimal point, that means it is a perfect square. So this is the same as, obviously, x squared, and this is the same thing as 3 squared. And since there's a minus between them, that's very important. Remember, the method up here was called difference of squares. We have to have a minus for this to work. This is a difference of squares. The difference of squares method is the easiest one. All you're going to do is take those and square root them, x minus 3, and then do the same thing but with the opposite sign, x plus 3. That's our factored form. I just square root this, and have one of each version, right? One with a minus and one with a plus. Like I said, you really have to check every single time if you can take out a GCF. In this case, we could not. In this case, we could take out a 4 from both. And if you do, you're left with, remember, dividing out an x squared and a 16. Once you take the GCF out, you're going to look at what's left. If there's ever just a regular number, you're not going to factor it any further. We're going to look at this piece right here. Can we factor it any further? Once we get down to where there's no exponents left, we know we're done with that problem. Can we factor that down any further? It is a difference. This is a perfect square. It's x squared. This is a perfect square. It's 4 squared. So we can break that down even further. If we're ever not going to break anything down, we're just going to bring it down with the problem. Then our x squared minus 16, since it was a perfect square, we'll do x minus 4 and x plus 4, just like we did above. Difference of squares is the easiest one to spot because it has to have a minus and it has to have perfect squares, and most people are familiar with the perfect squares. What do you think about this one? Take a second, look at it, and think about it. Everything's a perfect square. Is it a difference of squares? No, it's not. And if that's ever the case, you could just simply say that one is prime. I can't do anything with it. You'll have a button on MyLab or you'll have a button on Alex that will say this is prime. I can't break it down. How about the next one? There's no GCF. Is it a difference of squares or are they cubes? Well, 16 is 4 squared. X to the 4th is the same thing as x squared, believe it or not. Remember, x squared is like that. X to the 4th is like that, right? So it's just like the same thing twice. 81 is the same as 9 squared. So this is a difference of squares, and it's going to be 4x squared minus 9, 4x squared plus 9. Since the things we're dealing with still have exponents, right, we can still try to break those down. The one on the right is a sum of squares. We cannot break it down any further, so it's going to end up just coming down with us, 4x squared minus 9. Can we break down the one on the left, though? So this one right here. It is a difference. That's a perfect square. That's a perfect square, so I think you can break that down even further. If you do the square root of everything there, you get 2x minus 3, 2x plus 3. So the part that I underlined in blue, factor down into that part that I underlined in blue. And this is going to be my final answer, completely factored expression. This is an example of one where we broke it down, and then what we had, we could just even break it down even further. That does happen. All right, how about these? Do we have a GCF? We do not. Is that a difference? It's not a difference. It's not even squares. That's actually x cubed, so x cubed, obviously. The cube root, earlier I said if you do a square root of something, square root of 27 is not going to give you a nice number. It's going to give you a decimal. But if we did the cube root of 27, that's this on your calculator, it's going to give you 3. So it is a perfect cube, 3 cubed. And on your chart that you had, it said SOPS beside that. We're going to use that SOPS acronym now. All right, so you start off the exact same as you did prior. So it's just x plus 3. You're going to take the cube root of both of those. To get the next factor, though, you're going to have to use this acronym SOPS, which is square, opposite sign, product, which means multiply, plus square. Notice the first letters of each of those spells out SOPS, and that's why I have SOPS as the name of this strategy. All right, the way you do this, you just work left to right. So I'm looking at this thing right here, left to right. And what I'm going to do is square. So square left one. That'd be x squared. Opposite sign of that, that would be a minus. Product means multiply. Multiply 3 and x, and you get 3x. Plus, this every single time is just going to be a plus. Then square. We're moving left to right. We're on the right one now. That's a 9. That's our factored form right there. This right here looks like it can be broken down even further. And once we get to the next method, which is star method with 3 terms, we're going to see a way to break down things that look like that even further. But if you get something from SOPs, S-O-P-P-S, it's actually never going to be broken down even further. You can't ever break it down any further than that. I'm going to erase my SOPs down here and make sure that you have it written down so you can refer to it while we do this next problem. All right, the next one. Can you do a GCF? You always want to ask that first. You can, and you would have x cubed minus 8. Then you're going to look at this piece right here. Looks like it can still be broken down possibly even further. Is it a difference of squares? No, it's not. It's cubes, right? So with cubes, we do SOPs, and the first step is to cube root everything. X minus the cube root of 8 is 2. I know that because in the calculator, if you do third root of 8, it does just give you a nice even 2. Then I'm going to get my SOPs term here. So SOPs, if you have it written down as square, opposite product plus square. So moving left to right, square, opposite sign, the product of 2 and x, that's multiply 2 and x, always a plus, then square the right one. Again, that right-hand factor over there looks like it may be able to be broken down even further, but anything that you ever get out of SOPs is not going to be able to be broken down any further. All right, here on this page we've got ones with 3 terms. On that chart, you saw a star, and it had A times C, A, and B. Those all refer to the coefficients here with these. So A, B, C. If there's nothing there, it's understood to be a 1. We're just looking at the numbers here and not the variables. So in this case, A is 1, B is -4, C is 4. Let's start to fill those into the chart. So in our chart, that looks like the top A times C would be just 4. The top left and top right, 1 and 1, because they're A. The bottom is B, which is -4. And now here's the hardest part of the whole thing. You're looking for numbers that multiply to the top that also add to the bottom. So what multiplies to 4? 1 and 4. Will those also add to -4? That's the question. 1 times 4. 1 plus 4. That's 5. That does not add to that, so it doesn't work. How about 2 and 2? Does 2 plus 2 equal -4? No, it doesn't. What about -2 times -2? That also multiplies to 4, right? -2 plus -2 equals -4. So those do check out. As soon as you find one that checks out, you've got your combination. There's only ever going to be one combination. So the numbers that I'm using here are -2 and -2. -2, -2. The key here is to always try and simplify this like a fraction if you can. In most of them, you're not going to be able to. So 1 over -2, I can't simplify that fraction. So I'm just going to leave it exactly as is. Your variable is always going to go with the top number up there. So that my x, remember we were using x's here. If we were using m's, we'd put an m. If we were using y's, we'd put a y. This is where our two factors are going to come from. So that's 1x minus 2. Same thing as x minus 2. This one over here is also 1x minus 2. X minus 2. This one just happens to be the same thing both times, and so you could just write it as x minus 2 squared. That's also something that just doesn't happen very often. It's just a quirky thing that happens there every now and then. Let's try the same exact method on the next one. On all of these, once we do one example, what I would do is pause your video and go through and try and do it on your own and see how you can do. If you get hung up, then continue the video. So here, we've got 3 terms. Try and take out a GCF. There's not one. I'm going to make my star because I have 3 terms. I know 1, 2, 3 terms. I'm always going to try star. The top, A times C. A is 1 again. B is -3. C is -10. A times C is -10. A and A are 1 and 1. B is -3. I'm always starting with the top here. So can I multiply to -10? I can. 1 times -10 is 1 plus -10. -3? Nope, it is not. How about 2 times -5? is 2 plus negative 5, negative 3? It is. Oh, wow, we got it on the second try. So 2 and negative 5 are the magic numbers. Try and simplify that fraction, doesn't simplify. Try and simplify that fraction, it doesn't simplify. So our two factors are x plus 2. Notice this one was a positive 2 here. And x minus 5. Notice that this one over here was a negative 5, right? Whatever sign those bottom numbers have, they just keep. So these two right here are the factored version of that. I didn't mention this earlier, but if you ever took these two and multiplied them back together, you would just end up with what you started with. All you're doing is making like an equivalent, right? This is the same exact thing. This is just a different way to write that other thing up there. But there's a lot of things that we could use factoring for. It's just a very useful strategy in a lot of things. All right, three terms again. Can we break it down? X squared plus 19x plus 18. Again, I would try and do these on your own, then come back to the video. A times C is 18. A, B. Can I multiply to 18 and add to 9? I'm going to buzz through these because we've already seen the strategy once. But 6 times 3 is 18. 6 plus 3 is 9. So 6 and 3 are our two magic numbers. 6, 3. Those fractions don't break down, so this is the same as x plus 6. X plus 3. This one down here is going to work out the same way. The only thing difference is you can take a 2 out from the beginning. X squared minus 5x minus 14. Then when you do your star, negative 14, 1, 1, and negative 5, you're using the numbers in here because that's what we're trying to factor, right? This becomes a 1 because the thing in here is a 1. Negative 7 and negative 2 work. We always just bring down something if we don't break it down any further. And that is, wait a minute, this has to be a positive 2. And that's our factored form there. You can, this is an example of one where you can run into ones that just, they just don't break down, right? So 3 on top and 9 on bottom. Is there any way to multiply to 3 and also add to 9? There's not. 1 times 3, 1 plus 3 does not give you 9. There's no way to make that combination. So if you ever can't make the combination, it's just prime. All right, 4 terms. The last strategy here is grouping. That's what's on the right hand of that chart. The way that grouping is going to work is you're going to bunch up things in 2s, and then you're going to do GCF. It's just a glorified GCF here. So in that first group of 2, I can take out a 3x squared, and I'm left with x minus 9. I'm always going to keep that middle sign the same. Out of this next little bunch, can I take anything out? No. If I can't, then I'm just taking out a 1, x minus 9. If you can take something out of those, you absolutely will, and it would go here. All right, now you're going to look at these as an outside group and an inside group. I've got them labeled blue and red so we can have a blue group and a red group. There's always going to be one outside group, 3x squared plus 1, and one inside group, x minus 9. Again, if you took these two things and multiplied them back together, you would end up with what you started with. This is an equivalent form of what we started with. You also want to look at it and say, can I break this down any further? No, you actually can't. It's not a difference of squares. Same thing here. That one's all the way broken down. It can't go any further. One more example like that. We're going to keep that sign, like I said. All right, so first couple, can we take out anything? X squared, x minus 5. Here, we're keeping the minus. You can take out a 4, and so it's really like we're taking out a negative 4 here. So if I took out a negative 4, I would have just an x, and I would have a negative 5. You know you did something right when these two things match up right there. Again, we'll have an outside group and an inside group. And look at your things again. Make sure that you cannot break them down any further. In this case, this x squared minus 4 is a difference of squares. So I can break it down even further into x minus 2, x plus 2. That was the first method that we talked about. And then the x minus 5 just comes down by itself. It can't be broken down any further. That's the factored form. I've got one more example here because we didn't do any with star method where the first number was not a 1, and you do need to see that. It's important. On this one, if you did a times c is negative 30, b is 7, a is 2, and 2. Numbers that multiply to negative 30 and add to positive 7 would be positive 10 and negative 3, because positive 10 plus negative 3 would also add to 7. 10, negative 3. In this case, this one over here will not break down any further. This one over here will break down. The 2 and the 10, you can actually simplify that fraction to be just 1 over 5, right? 2 over 10 is the same thing as 1 over 5. You want to simplify that fraction as you could, if you can. So that's x minus 5. I wanted to show you that example. I wanted to show you at least one example where the first number was not a 1 and the fraction itself simplified. So that's all of factoring. Remember, you can always come back to this. This is a very important concept. Make sure you understand it. Come back to it as frequently as you need. And let me know if you have any issues.